Swayam Prabha. Digital India. Educated India.
Last example which we were talking was when we have a liquid mixture where the solvent is represented as B, which is in large excess, and into which we had added a small amount of solute, another liquid with small amount. And we had said that the Raoult's law is going to be valid for a liquid which are structurally similar. If you have a mixture of them, one being small and the other being in large excess, then the mole fraction, the partial pressure of the component A, which is the solvent, will be proportional to the partial vapor pressure will be proportional to the mole fraction, and the proportion to the, if you plot that, and the slope is going to be giving you the vapor pressure of the pure state. That is what we had talked about in the last class. This is what we had said. And if this equation is not valid, then we say that the non-ideality has said it. If the equation is valid, if any solution system follows this relationship, or it can be related to that equation of chemical potential, of this chemical potential relationship, then we say that the solution is behaving ideally. Now, another condition which we can look into, which we call as a real solution. So, an ideal solution, both solvent and solute obeys the Raoult's law. Mixtures for which the solute obeys Henry's law and the solvent obeys the Raoult's law is called as the ideal dilute solution. What does that mean? Once the solute is which is behaving obeying the Henry's law, and the solvent is using the same expression for the Raoult's law, then if such liquid is considered, then we say it is a ideal dilute solution. That means what we are dealing with is a real solution. Here we are dealing with is a real solution where the amount of the solute is very small. Okay, that means a real solution at very low concentration, the vapor pressure of solute is proportional to the mole fraction of the solute. Okay, but this constant of proportionality or the slope of that curve is not equal to the vapor pressure of the pure substance. Like if you have Raoult's law, what you have? You have the partial vapor pressure of that component A is proportional to the mole fraction of that component A, and the proportionality constant or the slope of that plot is going to be nothing but the vapor pressure of that component in the pure state in the solution. But here what we are talking about a real solution, but in very, very low concentrations of the solute, such that the vapor pressure of the solute is proportional to the mole fraction of solute in the solution. But the proportionality constant is not the vapor pressure of the solute at the pure vapor state, but it is some constant. This is an empirical constant. This is also an experiment which has been performed and formulated. That means people, Henry's experiments have been performed over a number of systems, and then only this equation has been established. So the Kb, what we say is the slope of the curve between the partial pressure of the solute B versus the mole fraction of solute B in the solution is the measure of the Henry's constant, which has a unit of pressure. Okay. Now, what is going to happen if you have dissimilar liquids? Then we have a strong deviation from Raoult's law. So, for an ideal solution, what you have, if I have ideal solution, the solute and the solvent in a mixture or in a solution will be following Raoult's law. So if I have a Raoult's law, then I should have a straight line of vapor pressure of the system versus the mole fraction of that system, of that component. And if it's a straight line, we say the Raoult's law is valid. But if you have a dissimilar kind of liquid, then it is no longer a straight line. It deviates. The green line indicates the deviation. Unless the solute is, say, much higher than the 0.9, some limit is supposed to be put. But that is what we are not going to look at. That is the deviation for Raoult's law. What happens when you talk about the Henry's law? Now, this slope, which we are talking about, we say in this, the partial pressure of the solute is going to be proportional to the mole fraction of the solute in the composition solution, and the slope of this curve will be the Henry constant. And this is going to be valid when the amount of the solute is very small. And when this equation is valid, then for the solute, and the solution is solvent is behaving ideally, like it is following Raoult's law. Under that condition, we say identify that solution as the ideal dilute solution. Is it clear? Is it clear? So if we want to write down the Henry's constants for various gases, you get the tabulated. I have a question here which I'm going to ask you. Very dilute solution behavior is the Henry's law. When means the solute concentration is very small. And what is this is the same diagram which I have just now shown. This is going to be the line for the Henry's, if it is following the Henry's law. This line for the solute should be the mole fraction, the vapor pressure of the solute equal to the mole fraction of the solute, and the proportionality constant or the slope of that line will be the Henry constant. And if you have an ideal solution, that is usually for a liquid system, a solvent system, that is going to follow the Raoult's law, and that Raoult's law states that the partial pressure of that component, the solvent, is going to be proportional to the to its mole fraction in the solution into the vapor pressure of that solvent in the pure state. Right? So if I can look into this, I can, if I want to simplify and do numericals, I can change the mole fraction to molalities and do the calculation, or even leave it in mole fraction, whichever is convenient for the particular numerical. Okay. Now, what is the basis of having this Henry's law? You see this, when you have a large excess of the solvent, then the solvent environment more or less remains the same. Okay. But the environment which the solute is experiencing, since it's in a very small amount, that is going to be entirely different. You can see the big particles are the solvent particles, and the small ones are the solute particles. For an ideally dilute solution, if I call the solution as ideally dilute solution, for which Henry's law is valid, for it is going to be valid for a solute which is supposed to be having an environment entirely different from that of the solvent molecules. You see, solvent molecules are majority. Solvent and molecule environment differs from the ideal condition of having a pure solvent, but that will not be so drastic. However, if you see it from the solute side, the solute molecules are entirely different environment from the pure. Had it been only the pure solute, whatever system you are taking, that environment compared to this is more drastic. So in ideally dilute solution, the solvent more or less behaves like a pure liquid. But the solute behavior is not like a pure solute. Okay. So these are certain numericals. Will you take down or will you do it? A solution is prepared by dissolving 1.5 moles of C10H8 in 1 kg of benzene. Vapor pressure of benzene is given at the temperature. What is going to be the partial vapor pressure of benzene in the solution? What does the Raoult's law state? Are you with me? Are you people with me?
Yes, ma'am.
So what will that be? According to Raoult's law, the partial pressure of partial vapor pressure of a component benzene here is the solvent is proportional to the mole fraction into the vapor pressure of the pure benzene. Vapor pressure of pure benzene is given, P star is given for benzene. And what we have to find out? What you have to find out the partial vapor pressure of the benzene in the solution. So what you need to find out? You need to find out the mole fraction. Right? All in this expression is to find out the mole fraction. You need to know the molecular mass of benzene. Can you do it? Similarly, how much is the chemical potential of benzene reduced at 25 degree by a solute that is present at the mole fraction of 0.1? This is also very easy. You have to find out the difference between the benzene minus the benzene pure, chemical potential of benzene minus the chemical benzene pure. And what was the expression which we had used? This is the expression. So I have to find out the difference between mu A minus mu A star will be equal to RT ln mole fraction of A. You have to use this expression, right? Are you people sleeping? No response.
No, ma'am.
No,
Like
ma'am.
there is lot of noise in my background. That's why I'm not responding.
But did you get the question?
Yes, ma'am.
Yes, ma'am.
Okay. So here, this is also a very easy question, but usually, what will be the partial pressure of methane is added to achieve a 21 milligrams of methane in 100 gram benzene. So you have solvent and solute both present here. What you need to know? You need to know the Henry constant. So Henry constant is given. I've provided the Henry constant. Can you find out the partial pressure of methane here? I think these are very simple problems. Just stay straightforward. Finding out the mole fraction is the only problem. So there is validation of these. There's a this is another numerical when the vapor pressures are given of two solvents, acetone and chloroform, with various mole fractions. You have to draw the diagram and confirm the mixture conforms to the Raoult's law for the component in large excess and to the Henry's law for the minor. Can you do this? What will you do? You have to show that the for the solute it is following the PA partial pressure of PB equal to mole fraction of PB into the Henry constant, and for Raoult's law it is going to PA equal to the mole fraction of A in the solution into the vapor pressure of the pure solvent A. You have to plot and then see. Okay. The diagram will look something like this, and here you can find out what will be the deviation. You can see the deviation, what it should be, and what is according to Henry's law, what it should be, and what you get actually. Okay, I'm not going to dwell on this. If you can do it, and this is I'm going to ask. Now, suppose we are talking about two liquids and we are talking about mixing. The requirement for that, we are saying we are going to not deal with more than two components. So let it be a binary system. So if it's a binary system, what it should be that the reagents which you are taking as two liquids, they should be, the solute we are talking about is a not electrolyte. They do not generate ion, and they are volatile, and they are non-reactive, do not react with each other. So if this is the basis of when we are talking about whatever properties of liquid mixture we are dealing with. Now two liquids suppose are there, A is the solvent and B is the solute. If it is forming an ideal solution, then whatever equation which we had followed, because since we are relating the vapor pressures to being equal to behaving like an ideal gas, so we can extend that concept of whatever G expressions we had got for the gas to be applied for the whichever system which we are dealing with, that is A solvent and B solute, both are liquids. So G initially, G finally, as you did in the G mixing process. So for all ideal solutions, for all ideal solutions, these are going to be valid. These are the expressions, if you remember. Okay, that means the delta G mix will be this expression, delta S mix will be this, and delta H mixing will be 0 if the solutions are ideal solutions. But if there is an interaction between, and the interaction of two solvent molecules and between two solute molecules, or between a solute and a solvent molecules are strong, then these are not going to be valid, and only thus those solutions are actually really existing. They are the real. For real solutions, these are not exactly going to be valid. These equations which we have derived for ideal gas behavior may not vary for this particular condition where you have interaction. Okay, and if this is there is an interaction, some amount of energy, which is whatever energy, enthalpy or entropy, whichever you are looking into, that will have some value, and that should be having some value which is when it is ideal, and the difference between these two is known as the excess, which is usually not discussed in the class second year course. But excess in excess in a liquid system or a composition of two liquids, a simple mixture of two liquids, the mixing process, whatever delta GH we had calculated, delta S mix we had calculated, enthalpy mix which we have calculated, those are all valid only when they are ideal solutions. And there is no interaction between the two solvent molecules or two solute molecules or between solvent and solute molecules. So for such cases, we say those are real solutions when there is interaction. And if there is interaction, the deviations in Raoult's law and Henry's law will set in. Okay. So we know the criteria for G should be negative, and for that we need to know the appropriate T and delta H and delta S. Now, what type of interactions can exist? There are usually three types of mixing processes, interactions in the mixing processes: solute-solute interaction, solvent-solute interaction, and solute-solvent interaction. All these delta H associated with these interactions need to be added to find out the delta H of the mixing process. And this is a real process. That means delta G mix will not be equal to 0. So if I have a diagram which shown to you very clearly, we are trying to separate solvent molecule, we are trying to separate the solute molecule, and we have a formation of solute and solvent interaction. Okay, one is being separated. Once the solute is being separated, then once the solvent is getting separated, and then you talk about the formation of the solute solvent interaction. What do you do? How do you calculate? This is not actually part of the syllabus, but just to give you a flavor, for enthalpy change of a process depends on the delta H. For these steps, of all the steps which are involved, the delta H should be summed up, or according to the equation, what should be the negative should be deducted, and then you get the value of enthalpy, total enthalpy of the mix. Okay, here I have identified what the processes where you are calculating this. You're calculating this, and these three processes, if somewhere you are given the values of solvent-solvent interaction, solute-solvent interaction, and solute-solute interaction. If these values are given to you, you can compute the delta H associated with the process. Okay. But what we have previously also seen, that the enthalpy is not the driving for the mixing process. When always whatever is being spontaneously done is guided by the entropy change associated. So if you have an increase in entropy, then the system energy is going to be lowered, right? If the delta S is more, that means randomness is more, delta S mixing is more, and the more the mixing is, you already know, whenever you have a system where the entropy is continuously increasing, that is going towards decreasing the energetics of the system. System goes to a lower energy. Yes, do you remember? So if you want to look into it, you have to see that you find out condition where by increase in entropy, you find out the entropy change. Now here you see the entropy change. Why should it be different for different two types of liquids, which is immiscible or miscible? will be decided by delta H of the solution in the final end product, right? Are you with me?
Yes, ma'am.
Are you people getting bored in the double lecture? Few more minutes, I'm going to stop now. So what I wanted to give you the flavor of is that the mixing process is entropy does have a contribution. We have calculated the way the flow chart is. This flow chart is not part of your syllabus, so forget it. You just to give you the entire interaction processes. Each will have a associated delta H, and these all delta H has to be added up for finding out the total delta H for the process, but for making a solution for any solution process. But this is not part of your syllabus, so just to know, you have to know that all these interactions associated enthalpy change have to be added. Now, next one is we have already discussed that the entropy of a system will always try to maximize, so that the in energy or the internal energy of the system gets minimized. So if I keep increasing the disorder, then there is a lowering of energy of the system. Okay, that is the things of spontaneous criteria for spontaneous change we have discussed. The entropy should be always going towards the maximum value. So the solution will be favored only if the entropy of the mixing is increasing, right? This is also which you have known. Now what happens, like how the Gibbs energy is affected? If you look into a molecule, suppose acetone is there, you have free lone pairs. This go and interact with the water molecule, then what will be the delta H value? So when you are talking about acetone is miscible or immiscible in water, we have to find out the delta mix, and then you will see that the acetone and water mix spontaneously. That means delta G is negative. So, but if you see hexane in water, what you see, they separate out as immiscible liquids, and for this the delta G is positive. Okay, we are going towards always a lowering of energy, so the value of G is minimized. So this is what I am just going to briefly tell you. I'm not going to discuss this in detail because these things are not really part of your syllabus, but since we are doing with it, I thought of mentioning whenever we have a non-ideality, we have discussed fugacity conditions. Similar to that, we have, suppose we have a mixing process which is ideally done and one which is in the mix, right, which is in the real solution mixing. So I have to find out what will be the whatever delta H or delta G change between what it was initially, that is the ideal state where it was behaving like an ideal solution, to which you have, which is corresponding to the non-ideal or a real solution. So if I can look into the expression for delta S, then I can write down the delta is excess associated with a non-ideality, because that is what is going to set in the non-ideality, is nothing but the delta S mix for the after the processing minus the delta S in the ideal state. So similarly, we can find out all the delta H excess functions and how the excess function looks. For enthalpy change, the expression is going to be something like this: the enthalpy change of the final mixing process minus the enthalpy change of the process which was where the gas was behaving ideal, and the difference between the two gives us the excess of enthalpy, excess of volume. Okay, so I think I'll end here. Similarly, for delta G, you can have an expression for delta G, delta S, and even delta V you can find out. So let us stop here and let us take up the colligative property in the next class. Okay.